Guys. All right. So yeah, Dr. Greer mentioned, my name is Megan Hinds. I'm in my second year with Dr. Paula James's lab. Thanks for being here. Happy Halloween. So I'm going to discuss my project, which is hopefully to explore the role of von Willebrand factor in COVID-19 associated endothelial cell dysfunction and thrombosis. So first, a brief background about COVID-19, because I know at this point we're all very, very familiar with it. It's caused by infection by the SARS-CoV-2 virus, which is a positive stranded RNA virus whose spike protein interacts with the human ACE2 receptor to gain cellular entry. It was first discovered in December of 2019 back in Wuhan, China, and by January 2020, it was already considered a public health emergency. So since then, there have been over 750 million cases worldwide, with over 6 million of those resulting in death. And that number now, since my last presentation, is very, very close to 7. So I wanted to use this graph as to kind of remind everyone what it was like in the early days of the pandemic, because I know it's not really at the forefront of our thought anymore. So just to orient you, the bottom x-axis is dates, and the orange is going to be the number of reported cases in Canada, and that's shown to the y-axis on the left. And deaths is in green, and that's on the y-axis to the right. And I think this graph does a good job of obviously representing the different waves and how the ratio between cases and deaths kind of differed for each. It's also important to note when vaccines became available. So that was in December of 2020. But again, if we can remember back, they weren't widely available, and that was kind of reserved for at-risk populations. So I know that I personally was very eager to get mine, and I wasn't able to get it until June of 2021. So this is reflected in the higher ratio of deaths in the first 2 waves. And then with Alpha and Delta, these had a higher transmissibility than the wild type. And it was also believed that they resulted in more admittance to ICU and more severe disease. And then finally, with Omicron, it had a higher transmissibility, but had less severe symptoms. So this is the time that there was obviously a huge influx in cases. And as a result, there was a change to testing policies in Canada. So while, of course, since then, there's been a reduction in COVID-19 cases overall, it's also believed that the number of cases is being pretty significantly underreported. So while 80% of COVID-19 cases were considered to be mild or moderate at the height of the pandemic, that still left about 20% that fell into the severe category. So severe COVID-19 can be characterized as the development of critical illness with COVID-19 and will require hospitalization, usually within the ICU, and a need for oxygen supplementation. So it's now well understood that severe COVID-19 is more likely to develop in people with older age, a more elevated BMI. It's very dependent on the patient's sex, as well as any pre-existing comorbidities, and of course, vaccination status. So I then wanted to talk a bit about the early research that was done and what people were seeing with COVID-19, especially with the clinical manifestations that were pretty striking. So there was the cytokine storm that I'm sure we've all heard about, which were these high increased levels of plasma cytokines. They also found that patients with severe COVID-19 were experiencing widespread microthrombi. So as you see here, there's 91% of this review paper, 91% of autopsies showed some form of microthrombi in that review paper. This led researchers to look into the implication of endothelial cells and specifically endothelial cell injury. So they found that there was a disrupted cell membranes, and then also that some endothelial cells expressed the ACE2 receptor, and that there was some evidence of viral inclusion in endothelial cells. So now I want to provide a bit of background on the actual endothelial cells, because as I mentioned, they're very much implicated in this COVID-19 associated thrombosis and therefore play a pretty big factor in my project. So endothelial cells are those cells that line our blood vessels. They are arranged in a monolayer that interacts on one side with the basement membrane, so namely the subendothelial collagen to which they're bound. And then on the other side, they interact with any circulating proteins, so things like cytokines, complement factors, anything like that. So they have quite a few functions, including things like the control of vascular dilation and constriction, which influences blood flow, They also play a role in inflammation, as they themselves can release inflammatory components, and they also can increase and decrease permeability. They are implicated in hemostasis as well as angiogenesis, so the formation of new blood vessels. With that being said, endothelial cell morphology and function varies greatly depending on not only whereabouts in the body they're found, but also the microenvironment to which they're exposed. So, of course, for example, they differ in arteries and veins, whereas the tight junctions between endothelial cells are much tighter in veins than in arteries than in veins. So another interesting, I guess, factor of endothelial cells is that they have these specialized rod-shaped organelles called Willebrand bodies. So these organelles will store and secrete various proteins, and they primarily store and secrete the ultra-large multimeric clotting protein, VWF. So that's what the image on the left is stained for, the VWF protein, and you can see that it's arranged within these organelles that look almost cigar-shaped. So within the Willebrand bodies, VWF multimers are stored efficiently in these long tubules that you can see as almost striations in the image on the right, and then again in the cross section. So interestingly enough, cells that do not express VWF do not contain Willebrand bodies. So now just to talk a bit about VWF, von Willebrand factor. So VWF plays a key role in hemostasis. And this is done through platelet recruitment as well as a chaperone for the coagulation factor 8. So the VWF monomer is composed of several subunits with binding sites that allow it to carry out these functions. So for example, VWF is capable of binding platelets through its A1 domain. It's also able to be recognized by ADAMTS at its A2 domain, as well as bind additional VWF multimers, which incidentally can either control or exacerbate its thrombotic potential. So VWF also complexes with factor 8 through interaction with its D3 domain, which prolongs the life of factor 8 in circulation. So this factor is involved in the intrinsic coagulation pathway, and without VWF, it's susceptible to rapid degradation and is unable to get to the points of vascular damage in the system that it needs to. This domain is also thought to be where VWF is able to interact with P-selectin, which is a cell adhesion molecule that VWF can adhere to basically once it's released from the cells. So VWF monomers are dimerized at the C-terminal cysteine knot, and then these dimers undergo further disulfide bonding to form these multimers. VWF exists in a range of multimers within the system, so it can be circulating in dimers, which is about 500 kilodaltons in size, but it can reach multimer sizes of up to 10,000 or more kilodaltons. And of course, the larger the VWF multimer, the more hemostatically active it is. So along with VWF, Willebrand bodies store and secrete a few other inflammatory and angiogenic agents, including, like I mentioned, P-selectin, Ang2, CD63, and interleukins 6 and 8. So it's important to note that Willebrand bodies, much like endothelial cells, can adapt really quickly to their microenvironments, and they will adjust their contents based on what is needed. So for example, if the cells are exposed to shear stress, they will decrease their Ang2 content. And if they're exposed to pro-inflammatory cytokines, they can actually increase expression of interleukins 6 and 8. So based on the lifespan of Willebrand bodies within endothelial cells, a single cell can actually have a pretty diverse population of Willebrand bodies, each with their own ratios of their cargo proteins. So we discussed the storage of these proteins in Willebrand bodies. So now I just want to talk about the actual secretion of them. So in vivo, endothelial cells become activated in response to various factors, including things like cytokines, hypoxia, vascular damage, and other agonists. So this is normally a well-regulated stress response that allows the cells to maintain homeostasis. But as you can imagine, chronic or uncontrolled endothelial cell activation can become pathogenic. So when endothelial cells are activated, their Willebrand bodies will migrate to the cell surface and then fuse with the plasma membrane in a few different ways. So the first form of fusion is, of course, single Willebrand body fusion, which is involving a single Willebrand body. So in this form, the Willebrand body will fuse with the membrane and release its contents into the lumen. And this includes, of course, VWF. It also includes its propeptide, which is released in equimolar concentrations to VWF, as well as P-selectin and smaller cargo proteins. So P-selectin will be released from within the Willebrand and kind of translocated to the cell membrane, where it exists as cell surface P-selectin, and then following proteolysis, it becomes soluble P-selectin within the bloodstream. So the lingering KISS fusion is interesting because it involves the fusion of a Willebrand body with the plasma membrane, and it forms almost a small pore that acts kind of as like a mesh, like it's a filter, and it doesn't allow the larger molecules to escape. So it only will release things like interleukin 8 and CD63, while the larger VWF molecules and P-selectin are maintained within the Willebrand body. And lastly, multigranular fusion involves the fusion of Willebrand bodies within the cell and then their subsequent fusion to the plasma membrane. And this form of fusion results in a massive release of all the Willebrand body contents. So this endothelial cell activation can be mimicked within the lab by the use of various agonists that kind of act on different pathways within the cell. So stimulation with histamine, thrombin, and complement components work to increase intracellular calcium ions, and this results in a release of Willebrand body proteins. In contrast to that, compounds such as epinephrine and vasopressin will work through a cyclic AMP-mediated pathway, which also leads obviously to Willebrand body exocytosis. Some studies have shown that secretion by the first pathway on the left will activate Willebrand bodies both on the periphery of the cell as well as more central, whereas when stimulated with epinephrine or vasopressin, it affects mainly the peripheral organelles. So now I want to kind of bring it all together and discuss VWF ADAMTS13 axis following secretion from the cells, specifically in primary hemostasis. So following endothelial cell activation, VWF is secreted from the Willebrand bodies in its ultra-large form. Now, a portion of this will remain tethered to the cell surface, and it can actually stick at various sites along the cell surface. And this is believed to expose many of its binding sites that I mentioned earlier, just based on the tensile strength between the points at which it's bound. It's also released from Willebrand bodies in this globular ultra-large form, which is kind of more like a meshed up structure. So it is actually a closed conformation, which conceals these binding sites. So it's not as hemostatically active, obviously, as the VWF strings. However, following shear stress, this globular VWF will unfold and expose these binding sites. So to control the thrombotic potential of this unwound VWF in circulation, the metalloprotease ADAMTS13, like I mentioned before, will recognize the A2 domain on VWF once this has been exposed, and it's able to cleave at this site. So this not only will release the VWF strings from the endothelial cell surface, but it will also process any circulating VWF into smaller, much less reactive multimers. So these multimers can then be directed to sites of injury where they're able to bind to the exposed subendothelial collagen and specifically recruit platelets to that site in order to form an initial platelet plug to stop bleeding. So I now want to discuss the VWF ADAMTS13 axis in reference to thrombotic microangiopathies because it kind of becomes relevant for my results and how I've set up my subsequent experiments. So thrombotic microangiopathies are a group of disorders characterized by hemolytic anemia, thrombocytopenia, and ischemic end organ damage caused by microthrombi formation. So I specifically want to talk about thrombotic thrombocytopenia purpura, or TTP, which is a thrombotic microangiopathy in which patients have a reduction in ADAMTS13 to below 10% of normal. And this can either be inherited or based because of autoantibodies against ADAMTS13. So in these cases, when there's an absence of ADAMTS13, you can imagine that there's an accumulation of ultra-large VWF within the system, and that this has a high potential of binding any circulating platelets. Studies of ADAMTS13 knockout mice have actually identified these long VWF string formations in vivo. And like TTP, like in the case of TTP, these platelet-bound strings are capable of causing microthrombi and resulting in a low platelet count. And finally, the VWF ADAMTS13 axis in severe COVID-19. So the similarities, of course, are that studies have shown highly elevated levels of VWF in these patients, and they've also found a marked reduction in ADAMTS13. So these observations may explain the type of thrombotic complications that are associated with COVID-19, including things like deep vein thrombosis, pulmonary embolism, and stroke. So the objective of my study is therefore to explore the pathophysiology of acute endothelial cell dysfunction throughout disease progression in severe COVID-19. And to do this, my project's been organized into 3 aims. For aim 1, it involves measuring biomarkers of the VWF ADAMTS13 axis and validating their associations with the clinical outcomes of my patients. And I want to point out that aim 1 is very much confirmatory at this point, because over the past few years, of course, COVID's been a very hot research topic, and it's been well established that certain biomarkers are able to predict whether patients end up in ICU, whether they experience certain complications, and even if it results in death. So I just wanted to basically look at that with my specific patient cohort and validate those associations. For aim 2, it involves the study of the effects of severe COVID-19 plasma on endothelial cell activation and Willebrand body exocytosis in normal endothelial cells under static conditions. So this is looking at things through obviously a very acute lens. These are otherwise healthy endothelial cells that are just going to come into contact with the contents of the COVID-19 plasma. And finally, I'm going to assess whether this severe COVID-19 plasma is capable of inducing VWF string formation, and if these strings are capable of binding platelets under physiological flow conditions. I also want to evaluate potential in vitro treatment for this formation of these strings. And so my hypothesis is, of course, that severe COVID-19 patients will have elevated plasma biomarkers of the VWF ADAMTS13 axis, and that exposure to this plasma under both static and flow conditions will induce an almost thrombotic microangiopathy phenotype, including things like VWF release, platelet adhesion, and endothelial cell injury. So this study was done in collaboration with Dr. Paul Kim at McMaster University and the COVID Beacon study. Patients were enrolled from the Hamilton General Hospital and Kingston Health Sciences Center, and the inclusion criteria were any adults over the age of 18 with severe illness with COVID-19, and exclusion was any known or suspected pregnancy. So samples were to be collected upon admission to ICU, and then periodically between days 6 and 15, and then finally at day 21 and beyond for patients who remained in ICU. And the biomarkers measured include VWF antigen and activity, VWF propeptide, factor VIII, ADAMTS13 antigen activity, and then using this data, hopefully identify some associations with clinical data. So there are 60 patients enrolled in the study, and I just want to highlight the dates at which they were enrolled. So these are not recent COVID cases. These were COVID cases pretty early on in the pandemic. And the time points that were collected are shown on the bottom image. So of course I have admission samples for all 60 patients, but that number kind of dwindles. Either they were discharged or they died, or they just weren't able to be sampled. And these are the baseline characteristics of my patients. So I just want to highlight where the majority falls for age, sex, and that's supposed to say body mass index, and vaccination status. So as to be expected, the majority of my patients are over the age of 60. They are male and have an elevated BMI. This is completely in line with all other studies who have found that the CDC has reported that over 80% of COVID deaths are in people over the age of 65. So the older population experiences much more severe forms of this disease. The majority male is also in line with other studies. So previous like MERS and SARS-CoV-1 were both far more prevalent in males, both with transmissibility and with the development of severe illness. And then, of course, vaccination status. So I also have information on the comorbidities, and I want to, of course, highlight the points that stick out the most. So almost half of my patients had pre-existing hypertension, and 38% of them had type 2 diabetes. Of all my patients, 80% had at least one pre-existing condition. And this is really, really important when looking at the data for these assays, because these are all factors that already are related to pre-existing endothelial cell dysfunction. So you could already assume that they may have more elevated levels already. So we also have clinical outcome information. And again, we looked at deep vein thrombosis, pulmonary embolism, and stroke specifically. So 35% of my patients experienced some sort of thrombotic complication, and 39% of them ended up dying due to COVID-19 associated complications. Of those 20% that died, 40% experienced some type of thrombosis and death, which isn't to say that they died of that thrombosis. I have cause of death information for 19 of the patients. And I just want to highlight that 3 of them did actually die of their thrombotic complications, which is pretty significant to me because it's not an isolated event, and it happened in my patient cohort as well. So this is obviously a pretty common clinical manifestation to some extent. So these are my results for the assays that I performed. So VWF antigen, activity, factor VIII, and propeptide. So as you can see, the highlighted yellow range is going to be the normal range for each of these assays. And all levels were pretty markedly elevated, with mean values peaking at around days 11 to 15. So this increase was sustained up to and beyond day 21, despite many of these patients having received a negative COVID-19 test at this point. So these are clearly features of some sort of a sustained endothelial cell activation that is very closely associated with severe COVID-19. We also looked at MTS13 antigen and activity, and again, the yellow range is going to, the highlighted range is going to be normal. So mean at MTS13 levels were below normal range, and this is in line with other studies that find an ADAMTS13 activity level of around 30% in COVID-19 patients. However, we were able to identify 4 patients that had an ADAMTS13 reduction to below that 10% of normal range. And that suggests that COVID-19 may induce almost a TTP-like phenotype. And again, that's characterized by this type of severe reduction in ADAMTS13. So we also identified significant associations, specifically between VWF antigen, activity, propeptide, and ADAMTS13 antigen, and the development of stroke or death in our patient cohort. So these values, specifically between days 6 and 15, were able to be associated with these outcomes, which highlights their relevance specifically during active SARS-CoV-2 infection. It also suggests that, like other studies have mentioned, these biomarkers can be used as tools to predict clinical outcomes. So for AIM-2, which involves the static analysis of normal endothelial cells exposed to COVID-19, I want to basically perform a quantitative and qualitative analysis of VWF and related Willebrand body cargo proteins in response to this plasma. So I'll be using endothelial colony-forming cells as a cellular model, and based on its physiological relevance, I wanted to use histamine as a positive control, normal reference plasma as a healthy control, and then, of course, severe COVID-19. So just a brief background on endothelial cells. So these are a progenitor cell population that can be isolated from peripheral blood. So it's a really non-invasive way of collecting samples and isolating the cells. You can see on the right, they have this distinct cobblestone morphology when grown in vitro. And of importance, they also express VWF as well as CD144. So these endothelial colony forming cells will be seeded onto collagen-coated plates and then grown 3 to 5 days post-confluency. They will be incubated with one of the treatments for 30 minutes. And then following that 30 minutes, the stimulants will be removed, the cells will be thoroughly washed, and then they'll be replaced with serum-free release media. So following that next 30-minute incubation, media will be removed, cells will be lysed, and then I did perform VWF antigen ELISAs using both the media and the lysates. And so this is the data for that. So as you can see from the first graph on the left, incubation with severe COVID-19 plasma stimulated high levels of VWF secretion compared to the normal reference plasma. Now, interestingly enough, although it wasn't of significance, the COVID-19 plasma also had a higher stimulant effect than even the histamine, which is the known Willebrand body agonist. So I also wanted to see if I could stratify patients into survivors and non-survivors and see if there was a difference in how that affected the cells, but there was no significant difference between the effects seen in cells that were incubated with survivor or non-survivor plasma. So for the next step, it's more of a qualitative analysis. So again, cells will be grown on cover slips in 3 to 5 days post-confluency and incubated with one of the stimulants. They will then be stained both extracellularly and intracellularly for VWF as well as P-selectin. And I wanted to include P-selectin because it is the cell adhesion molecule that's believed to anchor VWF strings to the cell surface. So I wanted to see if I could see any VWF outside of the cells and if that could correlate with where the P-selectin was found on the membrane. And this is the results for intracellular staining. So this is no stimulation. This is just a no stimulation controls. But I did want to show that I was able to identify P-selectin and VWF localization within Willebrand bodies. So P-selectin's in red and VWF is in green. And then this is the histamine stimulation. So again, I was able to see intracellular VWF as well as P-selectin in these cells. So this P-selectin obviously wasn't released from the Willebrand bodies as I was hoping. So this perhaps might mean maybe a longer incubation with histamine, maybe exploring some other agonists to use. This was done with a 10-minute incubation. And this is incubation with normal reference plasma. So interestingly enough, the normal reference plasma seems to have qualitatively similar effects to the histamine. There's still intracellular VWF and P-selectin within the Willebrand bodies. I do have to note that the colocalization of VWF and P-selectin was very heterogeneous with these cells, with the cell line I was using. So not all cells were showing P-selectin, and of course not all Willebrand bodies are showing it. So this is the results for extracellular staining so far. And again, this is all going to be the no stimulation on top. So as you can see, there's very little VWF staining. There's also no P-selectin staining. But the small amounts of green that you see could either be just from a basal release of VWF, or perhaps there's partial permeabilization with the PFA it was fixed with. And then this is the histamine stimulation. So again, this is extracellular VWF release following 10 minutes of stimulation. And you can see almost this like web-like structure on the endothelial cells. Unfortunately, there was no fluorescence detected for the P-selectin, so I wasn't able to see if that had anything to do with where these mesh structures were positioned. And the same with normal reference plasma. So again, normal reference plasma also did stimulate some type of activation in these cells, which was, of course, unexpected, but is kind of going to inform where I take this portion of the project next. So next steps for AIM-2, I haven't actually used the severe COVID-19 plasma yet because I do have limited supplies. So I didn't really want to dip into it until I had a really well-established protocol. And because I'm not seeing P-selectin exactly as I expected to, I feel like there's some optimizing that still needs to be done. I also wanted to include type 3 von Willebrand's disease patient plasma. So type 3 von Willebrand's disease is characterized by an almost total deficiency in VWF. So this would make the assumption that it has some other normal components within this plasma, but no VWF. So I wanted to see if that would warrant similar stimulation to the normal reference plasma. And lastly, I would want to try von Wende, which is a recombinant form of VWF, and see if that has any capability of stimulating the cells as well. So for aim 3 is the flow analysis of normal endothelial cells exposed to the COVID-19 plasma. And just as a recap, I'm looking for the VWF string formation and platelet adhesion in response to incubation with this plasma. So again, endothelial colony forming cells will be used as the cellular model, and they'll be stimulated with histamine, normal reference plasma, and severe COVID-19 plasma. So in this portion of the project, I wanted to also include TTP patient plasma because we saw so many similar biomarker levels with our COVID-19 patients and TTP plasma. And I wanted to see if they could be compared in any way, if there was some type of stimulation. Some studies have suggested that TTP plasma can stimulate cells, whether it be from the antibodies or some other component. So I wanted to include that just to get a better comparison. So again, normal endothelial colony forming cells will be coated onto channel slides, and they will be exposed to the stimulant. That'll be washed, and then they'll be perfused with diox-6 labeled platelets. So these are just fluorescently labeled platelets that can be added. And then we'll perform live cell imaging of the fluorescence. And you can see on the right here, so this is basically the exact protocol I'm hoping to use. And these are HUVEC that are now being perfused with these diox-6 labeled platelets. And you can see very clearly that the platelets do kind of organize along some kind of string structure. So the string quality will then be assessed by the number of strings on each lane, as well as string length and the platelet binding capacity. And I wanted to also include kind of a therapeutic option or a translational view of the project. So I wanted to also see if the perfusion of recombinant ADAMTS13 could work in processing these VWF strings that we may be seeing. So again, same protocol as before, but then we will perfuse them with the recombinant ADAMTS13, and then the efficacy will be assessed based on time before proteolysis. So next steps for this one, it includes everything. So for the TTP plasma, we're waiting for samples from the hospital because when patients are in need of a plasma transfusion in order to get normal ADAMTS13 levels, it's a very abrupt, immediate thing. So we're kind of on call for when there is a patient coming in, and they'll be able to take off a bit of plasma before they start with the plasma exchange. So I wanted to run these experiments as alongside each other as possible. So I'm just kind of holding out on that until we get the call that there's plasma for us. So now I'd like to discuss a few limitations to this study, of course. So first, as I mentioned before, I do have a limited plasma supply. So because of this, there's a few additional biomarkers that I think would be really valuable to measure, which I haven't been able to measure yet. I'm not to say that I won't be able to, I just want to be able to run my cell experiments with the plasma before dipping into it for more of these assays. So because I have a focus on P-selectin with my confocal imaging, I think it would be a great value to measure soluble P-selectin in the plasma samples. And not only in the plasma samples, but also in the cells following stimulation with the severe COVID-19 plasma, because I wasn't able to see surface expression of P-selectin in my confocal images. So I want to be able to see if that P-selectin could somehow have been released into the media as well with the VWF. I also obviously would like to create a more robust cytokine profile for these patients because we know that cytokines are majorly implicated in severe COVID-19, and they also act to activate endothelial cells. It's also important to note that some cytokines can also affect the activity of ADAMTS13. So I think it would be really valuable to be able to find any associations between ADAMTS13 levels and things like interleukin-6, which is thought to maybe affect the expression of ADAMTS13 as well as its ability to cleave VWF. I also want to point out that just based on the nature of this study, I'm not able to have baseline data for the patient biomarkers. And And this would be really valuable because I do have an already sick population with a lot of pre-existing comorbidities. So it would be nice to, as a comparison, see already where they're sitting with things like VWF, and then be able to compare these really high levels that I'm seeing after they have COVID-19. So I wanted to wrap up this presentation, I guess, with a brief discussion about the impacts, because this stage of the pandemic, it kind of seems like maybe I'm straddling the line between like novel and maybe irrelevant, but there are some really important things to be learned from these studies still, specifically to identify very targeted therapeutic options for these treatments. So instead of throwing everything we've got at these patients who are experiencing thrombosis in hopes that it will just either, whether it be an anticoagulant or something like that, I think being able to have a targeted response to patients who have low ADAMTS13 levels, like recombinant ADAMTS13, would be of benefit. So these images on the right are just from a paper that basically administered recombinant ADAMTS13 to mice who had been made ADAMTS13 deficient. And you can see that obviously not only increases the ADAMTS13 activity, but it also reduces the amount of high molecular weight markers in these mice. So this recombinant ADAMTS13 is capable of processing these ultra-large multimers. I think it's also important that for these kinds of studies in uncovering the mechanisms of endothelial cell activation that can be applied to future pathogens. So when COVID first was identified, there was a lot of reference to past pandemics, and that really led people in the right direction in terms of figuring out treatments and how to manage it. So I think that, unfortunately, I didn't ever think there would be a pandemic in my lifetime, but now I'm kind of thinking maybe this won't be the last pandemic of my lifetime. So I think this will be good to be able to be applied to future viral outbreaks. That's it.
Thank you. I'm sure Megan would love to have some questions now. Danielle?
Great talk. Thank you. I think you kind of touched on this already, but in your biomarker study, those normal values, were those like normal healthy like volunteers, or were they patients that had some of the morbidities with the
No, so that normal range wasn't any actual specific patient assay. It was just like the normally accepted ranges for those assays. But yeah, it would be nice to compare it to a patient with hypertension or something like that. Yeah.
So I was very curious about your I guess it was spinning disc. So are those, how do you label that fluorescent material? Is that platelets that we're seeing there?
Yeah, so
Okay,
those are
those
fluorescently
dialed.
labeled
Okay.
platelets. So from what I understand from the protocol, they have to be you have to collect the platelets very fresh, so it has to be labeled the same day basically.
Yeah.
And then through that you're able to perfuse them over top of the cells.
Okay, and they get sticky and
That's the plan. Yeah, let's hope
so.
so.
Other questions? I got lots. Okay. Yeah.
In your characteristics of the patients, there was a little footnote that video types of the data will be collected. So why do you single that out? Is there like some reason to talk about that specifically in this context, or?
For sure. So in reference to what we're saying about like hypertension and how we don't have the baseline data, so ABO blood type does actually affect, well, it can affect VWF levels in patients, not patients, in people. So people with O type blood actually have around 20 to 30% less circulating VWF than people with A or O. So again, if we had that information, that would be interesting to see if maybe some of the patients with higher levels of VWF were in fact A or B type, and that would maybe account for that discrepancy. So unfortunately, we don't have that information, and I just don't have enough plasma to do that. So just be a mystery, I guess.
So do you have a list of suspect components to the serum?
Yeah. So that's kind of what I feel like my life has become now, is just a process of elimination of what it could be. So, I mean, I think the cytokines have a really big factor in it, of course. I mean, I want to explore maybe even the potential somehow that BWF could be implicated in this, or if it's more a cause as opposed to an effect. So I want to be able to cross that off my list
Okay.
for sure. I think it's a combination of a lot of things. Unfortunately, with COVID-19, there's just so much going on. They have so many markers of inflammation and inflammation and thrombosis. So I think majorly cytokines. Yeah.
So, but are people trying to, when you talk about what kinds of treatments would be available for patients under these conditions, are you talking about trying to come in with neutralizing antibodies to some of these? Are there candidates out there that are being looked at in that regard?
I know that there are candidates, a few different drugs that act more so on controlling things like EC activation so much, that have been looked at. I know in the early days with the cytokines, they were throwing out corticosteroids just as like an immediate, just to stop. But there's so much research on it that it's at times overwhelming, but
have things like anti-TNF alpha, which I guess is clinically available, have they been tested? Tried?
I'm not sure about that one.
Okay. David?
Very nice presentation there. Yeah. I have a couple of questions if I can. So, I mean, as you alluded to, the key thing is what is making these endothelial cells misbehave, activate. So, is there any evidence the virus is responsible for this? I mean, do endothelial cells express ACE2 receptor?
So this is where the research says that it does. A lot of research has said that endothelial cells are capable of expressing the ACE2 receptor, and that they have found direct evidence of viral infection into these endothelial cells. But then again, I've also seen studies that say that they are unable to be infected with the virus. So I've seen studies where they actually will incubate the cells directly with this COVID-19 plasma, and it doesn't directly infect the cells. So I am more of the camp that it is the environment in which the disease creates that causes the activation, as opposed to direct infection, especially with my static experiments that show that under these acute 30-minute incubations, they're having this type of response. Yeah, that's my opinion.
You showed a picture, I think, in your M2 where you put COVID plasma onto ECFCs and you got an increase.
So that was normal reference plasma.
It was normal.
Oh, sorry. Yes, you're right. Yeah, in the first part.
Yeah.
Yeah.
So do you know, did that plasma contain virus? I assume not, but you know. And what was the VWF level in that plasma? Was it elevated?
Yeah, so the plasma was definitely elevated. So for that portion of the project, I used specifically samples that were collected between days 6 and 15, which, if you remember, was when I saw the highest levels of VWF in these patients. So I wanted to use that as the plasma because that had been correlated with the clinical outcomes. So they definitely had the highest levels of VWF in them already. Unfortunately, I'm not able to determine if they had any virus in them. At least last time I looked into it. I don't know if things have changed, but they don't like us doing anything that resembles replicating even the viral RNA, anything like that.
So your introduction was really informative. I love the part about the different mechanisms of viral antibody fusion and release of content. Food for thought. How is that all determined? Is that all electron microscopy or other sorts of methods?
Yeah, so it's all that type of electron microscopy imaging that they're able to identify that. And they can also measure this, they measure the pH changes as well outside of the cell. Yeah. So when with the lingering KISS fusion, for example, it has the smaller pore, there's not as much change outside of the cell. So
have you guys tried to see that using I guess the very high powered microscopy approaches that are available now?
I haven't. I have to say that with the microscopy stuff, I'm pretty still getting acquainted with that. So I'm not, haven't looked into that yet.
I'm just wondering if you can see some of that stuff with
Mhm.
turf approaches,
Yeah.
that sort of thing.
Yeah, because when I was thinking about why I wasn't seeing P-selectin outside of my cells, that's why I kind of dove into that a bit to try and explain that maybe there's a certain type of fusion event that's happening that's not allowing that P-selectin to escape, but because there is extracellular BWF, I find that unlikely. So I think it's maybe just a matter of optimizing my protocol a bit.
Yeah, because you think there'd be an awful lot
Mhm.
there.
Yeah, exactly.
I think similar thoughts actually, you know, in your implementing, especially that part of your background, which is different than the last kind of presentation. It was really interesting. And so I was thinking exactly what Peter was thinking in terms of, is there a way for you to actually try to get at that level of detail in
Mhm.
terms of what you can see here?
To see what's happening.
It's worth us thinking about and exploring because it would be fascinating to look at.
Yeah.
I had a question about the male predominance, which has always been a sad feature of, I guess not for me, but
Yeah, I think we're fine.
yeah, I mean, a sad feature of all of it. And are there explanations for why that might be?
Yeah, so there's a few different studies that I've identified things like slower viral clearance in men. They think some people say that maybe it has to do with like the X chromosomes in women aid in their like immune systems a bit more. It's like a very general answer, but there's a few different things that they see specifically in COVID in men versus women. So women have a faster and more robust response basically, and men have like slower slower viral clearance. So.
And is any of that age related? Just thinking about some of what we see in women premenopausally and then postmenopausally and things like cardiovascular disease and hypertension, the curves start to get closer together postmenopausally.
Mhm.
That maybe there's something protective about estrogen. So I was wondering about that in the context of what
I haven't seen anything specifically about estrogen, so I'm not sure.
But interested, I mean, David Ladd is looking at, you know, the influence of estrogen on BWF and just crossed my mind as something I'm thinking about.
There's so many facets
Yeah.
to it. There's so many angles at which to look at this type of COVID-19.
You were doing some statistical correlation analysis on, I guess, stroke and death.
Mhm.
You have enough events there to actually do
So true with the stroke, but I had to speak with someone about it because again, stats isn't exactly my strong suit, but the death correlation was was enough. But I agree with the stroke, there's just not enough people.
Yeah. Natasha probably has questions for you, but she's too shy to ask. I'm not part of it. Well, in particular, and it relates to things like seeing P-selectin on the surface of cells, but being able to catch those events. And in some applications, you may be able to use some kind of a cross-linking approach. And you're fixing with paraformaldehyde, presumably at some point.
Yeah.
So, how much paraformaldehyde do you throw at these cells when you're trying to trap that content, say, on the surface of the cell, and don't have it wash away when you're after you're doing staining?
I guess, yeah. So then would you say possibly then decreasing PFA?
Well, that's the sort of thing
might
that we
be
have a long discussion about.
Putting together a protocol like action today, so this was quite relevant to see, but I haven't actually tried it myself yet, but seeing some of your data has me like stewing a little bit. Obviously it goes into the nitty gritty details like set formaldehyde.
For sure.
For language and for everything, how long before you fix everything like that. So I'm giving it a push.
You should put that my way. You should, because like I said, I'm not super familiar with this type of cell imaging and stuff like that. So this is kind of something I've just been learning myself. So I've obviously tried tons of different things just to like optimize the protocol as much as possible.
Yeah.
So yeah, anything, I was gonna say, just send it my way. I'll try anything.
Yeah, because some things you can see very beautifully
Mhm.
as far as the content, the wild lady content of this helium cells. It's great, but I guess that's probably an easier catch because they're in the cells and probably in the context of fixing them, they're cross-linked to the cytoskeleton. They don't go anywhere. Stuff that's on the verge of leaving.
Yeah.
A little bit more delicate.
Was there just the one cell type? I can't remember exactly that you were looking at.
Yeah, so I just have the one cell type and they're all from the same patient. So I wanted to kind of keep it as consistent as possible. So just the endothelial colony forming cells.
I didn't see any questions.
There's one question.
Oh,
Okay.
sorry, I'm bad with this.
You see them there? Is it in the chat?
Okay, so it's Orla. She says, how are you going to address the fact that your reference plasma is a pool and therefore represents all blood types? Are you going to provide these plasma from a single patient on your cells? Okay, so basically just normal reference plasma is pooled and the COVID-19 patient plasma is individual plasma, which we did discuss earlier when we were trying to figure out why the normal reference plasma was creating some form of activation. So yeah, that's a great point. And we were considering also just using a single patient normal plasma instead of the pooled. The nice thing with the pooled is that it does have a bit of a profile already in it. So we do kind of already know a few different components of it. But again, that can be measured in an individual patient.
Okay. Any last questions? If not, join me in thanking Rebecca for